Hello and welcome back to Calculus 3. This is going to be exam 1 review because in your infinite wisdom you picked to have an exam, right? So now we are going to talk about the exam. First off, the exam is on chapter 11. I don't know, a bit dramatic there. And that's going to be 11.1 through 11.9. We're looking at 10 questions. You know, for simplicity, each one is 10% and so on. So 10 questions, and it covers all of the sections. Now that is going with computing vectors and so on. So let's see. Working with vectors. Now this is adding, subtracting, scaling, converting, figuring out the components, vector notation, proper vector notation, and all of that kind of stuff goes in working with vectors. And then we have dot and cross products. Then we have the application of dot and cross product, which would be work and torque and projection, all of that good stuff. So working with vectors, dot and cross products, and then application of those. Then we have a vector valued function R. Then we have applications. So application in terms of position, velocity, acceleration, speed, and that's all vector valued function. I'm going to single out the unit vector t because it's important. You absolutely must know how to find this vector. Working with vectors also involves unit vectors. So addition, subtraction, scaling, components, notation, unit vector definition, all of that stuff that was in 11.1 and 11.2 is in the first bullet point. Then we have motion in space. And I'm just going to link that up with the previous one. You only have that one equation to worry about, which is the free fall. The rest is all in here. So the only thing that you are worrying about over here is the free fall, and that's a 2D case, right? So that's all. No, it's either 2D or R2. So 2D. That's the only thing you're worrying about. The rest is length of curve, we have 3 flavors. We have the Calculus3, the rectangular one with x and a y, and then we have the parametric and polar. Those are the 2 new ones that we brought up. And finally we have this lecture from today, which is the lecture on curvature and normal vectors. You must expect at least one calculation of the cross product. You must expect one calculation for derivatives and integrals of vector valued functions, which is actually a whole section on calculus of vector valued functions, right? So you need to be able. Now that could all be within application. So if I give you, let's say, a position function and ask for velocity function, you're differentiating. If I give you acceleration function and you and asking for velocity or integrating. So all of the Calculus 1 concepts pushed into the vector R, which is actually now 3 Calculus 1 concepts in one.
So you said one calculation for cross product, and what was the other one?
Well, the cross product is the long, right, calculation. You definitely have calculation for tangent vector. You definitely have a normal vector, right? So all of these, the things that you see on the homework, obviously, all of those are there. Why I single out cross product? I single out cross product because cross product is going to be used later for tangent plane and so on. So cross product will live on. Our equation R will be back briefly in chapter 12 and then also in chapter 14. So a lot of these things are going to live on as we go through this. So think about it. Length of curves, there's one problem. Curvature, normal, tangent, cross product, some kind of vector value thing with the calculus, and then application of that, and then one of the word problems application, the work torque or something like that, or projection. And then a question that asks you to either state the formula or state the concept. For instance, define a vector valued function, right? That's one of the, or what is the formula for curvature? Or what is the formula for unit tangent vector? What is the formula for unit normal vector? So technically, when you look at the page 581, you look page 581, what's the formula for unit tangent vector? What's the formula for normal vector? What's the formula for curvature? Right? What's the formula for, I don't know, speed? Formula for speed, well, that's the magnitude of velocity, and velocity is the derivative of r. Right, so that's the kind of gift problem, because you're just stating things that you absolutely must know to do anything on your exam. Yes?
When you ask those questions, like, is it all you want formula, or do you want justification, or just...
Well, it's not an honors course, so the proofs are kind of suppressed into one location. So not for now. So yeah, it's mainly stating the formulas. Because you are using formulas as engineers, right? You guys primarily worry about computing something rather than proving it's mathematical. Right now, you're a math major, so you might be considering the honors option because it gives you more. It lines up better with what you are a part of. So that's pretty much that. So 10 questions, and I would say 1 or at most 2 applied problems, which are word problems, and then everything else is just boring calculation. Normal vector n. Apparently I found the easy one and did it in class by accident. So, you know, generally you will see when you start working on your homework, these problems take a very, very long time. So some of the test-taking skills should be there in terms of, well, let's solve the easy problems first, which means look at the entire test and then solve the problems that you are very familiar with, that you like the most immediately, so that within 15 minutes of the exam you can have about half of your exam done. And then focus on the rest of the stuff that either takes long time, like anything that contains cross product might take long time. Normal vector and curvature clearly should take long time because it's just a lot of calculations there. If you have some simple integrals and derivatives and things like that, that should be short, so those problems should be done quick. Also, length of curve. I'm not going to be really focusing on, integration, like Calc2 integration, those really extraneous cases where you have to use, partial fraction decomposition, which leads into trig substitution, or something like that, along those lines. I'm going to primarily focus on, whether you know Calculus 3 material, because you've seen that you have a function and then you have to differentiate twice to get the other things. If you're here, you have to integrate twice. Right, those are all Calculus 1 and Calculus 2 concepts on how to do the problem. Calc 3 is more of a concept of what it is and pushing it. Let's not forget the equation for the sphere, equation for the line, right? All of those things, because some of the, good, this is giving a suggestion. Can you figure out what are the intersection of like if the line and a sphere intersect, right? Or a line and a plane intersect, or two lines, do they intersect in space? Like all of these things, because you can have, see, in 2D, there is only one way to have lines not intersect. Parallel lines, very good. So when you are in a 2D realm, two lines, if they are parallel on the flat surface, they don't intersect. On a curved surface, they do intersect. But on a flat surface, a 2D surface, parallel lines do not intersect. Now look at this. This line and this line are clearly not parallel. Do they intersect? No, because look, they miss each other in space. You see that? They don't intersect. But they are not parallel. They are not parallel lines at all. You can actually put this one this way, this way, this way, any way you want, right? They don't intersect. They pass by each other, right? So, what are the conditions for the lines to intersect in 3D space? I said this on a day one. There's no way for me to do every single flavor of every single problem, because there's way too many combinations once you move to 3D. So, the idea of two lines being parallel in 2D, right? For 3D, right? None of these lines intersect. And that's already infinitely many combinations, right? So, question is, do line 1 and line 2 intersect? What is the angle between two lines? So I give you two lines in space. How would you find the angle between them? The dot product. I give you two lines in space. The dot product works with vectors. So how would we do that? What was that?
Is the dot product divided by the magnitude of the vector, and then the arc sine or arc cosine? Right?
Yeah, but I'm giving you two lines, and now you guys are not wrong. You're getting there, but what is the link that you need? Like, how do you convert one into another?
Or the x1 minus x0 something like that.
Okay, is there an easier way?
Parameterize the line.
Well, I will give you a parametric line. But how do you get a vector out of it? Because you're telling me, use the dot product with the inverse cosine, so 100% of what you said, guys, is true. My question is how? I'm going to give you 3 minus 2t, comma 5 plus t, and then comma 6t. Where's the vector there? You see, that's the concepts of Calc 3. Yeah, the dot product and all of that cool, cute stuff. But I'm actually asking you a mechanical engineering question. All right? Yes? Well, that's a way to do it. It's a lot of work, but you see, this is why it is so important in calculus to actually learn the definition and the theorem first before you start working any problems out. Because once you realize that for the linear line, right, the straight line, your vector r is given as x0 plus at, y0 plus bt, z0 plus ct, right? When you have this definition for it, this A, B, and C is actually a 3D slope direction. That is your vector V. And if you go back into lines and curves in space, what was the first thing that we talked about? Well, second thing we talked about, lines in space. Look at a green line over there. That's vector V, and its components are A, B, C. So if I give you a line in this form, your vector is included. There's A, B, C. That's the vector. That's the direction and the magnitude of the vector. So now you have a vector, then you have another vector from the other line also given through A, B, C, and you can run your cross products and dot products or whatever you want to find the angle between the two lines. And that's going to continue later on, because the later the vectors are going to describe planes and all of that kind of stuff. So if you want to see, now this has nothing to do with intersection. This is the angle between two lines that we know are intersecting lines, right? Now also figure out, right, what it means for line to intersect. Now you have two parametric equations. Like, what is the common sense thing that has to happen in order for two lines to intersect? They have to equal each other for the same t, because parameter t is what drives. So there has to be a point in space at t equals, let's say, 5 seconds, and both of the lines are going to have the same value at that point. It's the only way to have them intersect, right? If they share the same. So there are ways to figure these things out. I can't teach every single example, because we would still be probably at 11.3, right? And the first third of a course. Yeah, wow. We're almost at one third of a course, guys. How about that? Next week is half of the course. It's cool, right? Honors for this exam. We said they have the proof for those properties. So I will say prove the property and then list one or two properties from the list of vectors, properties of vectors. If you are considering honors option because of the math major thing, you can also pay attention now. If anyone is interested in honors option, we can still add people, obviously. So we have the proofs for those. I think I did one or two in class. Then we have the proof for like derivation of the parametric and the polar for length of curves. Those proofs are cool. Then we have the curvature conversion proof. It's just a calculation. It's a one line. Then we have proof that the curvature of the straight line is 0. Proof of the formula for curvature for a circle, that it's 1 over radius. That's also a cool thing. And there was one more thing that was there that was really, really good. Oh yeah, the derivation for, that's listed in a book, derivation for the projection. That's that. So honors option will have 2 extra questions. So regular exams 10 questions, honors option 12 questions. It adds the two proofs. And as you can see the list, these are all very short proofs that do not involve a lot of writing and a lot of things. Each one of these could be 4 or 5 lines. Like The proof you guys have on your lab with the A and B stuff, like that's really long, right? That one takes long time to work out. Yes.
How long did you say we have for the test? Hour and 20.
Very good.
And then for tomorrow, what class test would you like?
Well, whatever you bring, but I'll have, so tomorrow we're going to do 12-1, and we're going to have more review and more lab. And then after the exam, we'll have 12-2. And then we'll try to finish chapter 12 the following week. Because following week is half of the course is gone. We have chapters 11, 12, 13, and 14, right? 4 chapters. So it makes sense that at the end of week 3, which is half of our course, we are done with chapters 11 and maybe 70-80% of chapter 12. Any other questions, concerns regarding the exam? If you have any particular problems, please bring them tomorrow so that we can solve problems if you have problems, right? Make sure you go to that practice exam, see what's up over there. Don't forget your quizzes online. Don't forget about the study session that is tomorrow after class. Yes?
Can you put up the homework for 11-8 and 11-9? I don't think it's up.
It is now.
Oh, it is?
Yeah.
Okay. Thanks.
Magic. All right. So I'll see you all at some point in life.